Hello everyone, and thanks for watching Edupedia World videos. So in this session of states of matter, we'll finally talk about ideal gas equation. So we'll look at the complete equation and all the variables inside it and how to apply this equation in various situations. Okay. So before we start with the ideal gas equation itself, we must know something called combined gas law. So if you remember, we have already seen Avogadro's law, right? And what did Avogadro's law said? That volume is directly proportional to number of moles, right? And then we have also seen Charles' law. What did that say? That volume is directly proportional to temperature. And what about Boyle's law? Boyle's law says that there is an inverse relationship between volume and pressure. That means volume is inversely proportional to pressure. Okay, so basically if you simply combine all these three equations, what you get is that volume is directly proportional to N into T divided by P. Okay, so that is your volume is directly proportional to number of moles multiplied with temperature divided by pressure. Alright, so to remove this proportionality sign, I can introduce a constant of proportionality, or for now we can continue to deal with this proportionality sign, alright, and see where it gets us. So basically I can rewrite this equation in the form that P into V divided by T is directly proportional to number of moles, alright, because even pressure, temperature can be dependent variables. They need not have to be independent variables necessarily, right? So this means that if number of moles is constant, that is I have a container in which I have fixed the amount of gas present inside. Okay, so these are the only molecules of gas which will be present inside. Then N gets fixed, and if N gets fixed, this equation reduces to the form that PV by T is a constant. Alright, for a fixed amount of ideal gas, the ratio of pressure into volume and temperature is always a constant. Okay, this means if initially my container had a pressure of P1, volume V1 and temperature T1, and if I decide to change, let's say, any two variables, say I decide to change pressure to P2 and temperature to T2, okay, then volume will automatically adjust itself to a new value V2 as per this equation. Okay, and this equation PV by T is a constant, or P1 V1 by T1 is equal to P2 V2 by T2, assuming that the amount of gas inside the container is fixed, is called combined gas law. Okay, that is, it combines the various gas laws that we have studied in previous sessions into one single law. Okay, and using this equation we can solve various questions where instead of two, all the three variables are getting changed. Okay, up to now we were only changing two variables at a time, like pressure and volume, or pressure and temperature, or volume and temperature, and so on. But now we have decided to change all three, and this equation helps us to solve the problems where all of these three are changing. So if you know any of the five variables out of these six variables over here, okay, there are six variables, P1 V1 T1 3, and then another three variables on the right hand side. So if we change any five of them, then we can determine the sixth variable using this equation. Okay, so that is it about combined gas law. Now let's talk about removing this proportionality sign from over here. Okay, and let's see where that gets us. Okay, so from the previous slide we have that PV by T is directly proportional to number of moles. Let's get rid of this proportionality sign now by introducing a constant of proportionality, say R. Okay, let's represent the constant of proportionality with capital R. So here R is a constant, and its value can be said to be equal to ratio of P into V and N into T. Okay, so this R, it so turns out is independent of the type of ideal gas that we have. Okay, so whether we are assuming carbon dioxide, methane, ammonia, nitrogen, as long as their behavior is of ideal kind, the ratio comes out to be same and equal to capital R. Okay, so it is not exactly dependent on pressure or temperature or volume or even the amount of gas. Okay, and this constant is hence known as universal gas constant, because first it is applicable for ideal gases only, second it is universally applicable to all the ideal gases that we can take into account. So how do you calculate the actual value of R? So you simply calculate the values of these four variables. Okay, in fact we have already seen the value of volume or molar volume, right, for different conditions of pressure and temperature. We have seen the value of volume of 1 mole of gas at STP, at NTP and at SATP, and then using those values we can calculate the value of R in this equation. So let's see what values do we get. So in SI unit, okay, so in SI unit I will have to substitute pressure in terms of Pascal, volume in terms of meter cube, N is always in moles, and temperature is always in Kelvin. Okay, do remember that. So only thing that you can change over here is the units of pressure and volume. So by changing that, we get that in SI unit R is 8.314 Pascal meter cube per Kelvin per mole. It's pretty clear. P has the unit of Pascal, volume has the unit of meter cube, and N has the unit of mole, and T has the unit of Kelvin. So Pascal meter cube per Kelvin per mole, and Pascal meter cube can also be equated to joules, which is the unit of energy, SI unit of energy. Okay, so hence R can also be written as 8.314 joule per Kelvin per mole in SI units. Okay, but the thing is we don't usually use SI unit. Okay, in case of R it is quite common, but even more common is when pressure and volume are taken in ATM and liters. Okay, so if we take pressure and volume in liter and ATM, we get the value 0.0821 liter ATM per Kelvin per mole. Okay, and if you convert this joule into calorie, okay, if you decide to convert this joule into calorie, then how do you do that? So how many calories is how many joules? Okay, so it's a simple relation. 1 calorie is 4.18 joules, right? So you just use that relation to convert joules into calorie, and you get that R is equal to actually 1.987 calorie per Kelvin per mole. We can approximate this value as R is equal to 2 calorie per Kelvin per mole. Okay, and lastly, one last value of R which we have to see is in bars liter per Kelvin per mole. So instead of ATM, if I decide to use bar over here for as the units of pressure, okay, while maintaining the unit of volume as in liter, okay, and temperature and number of moles is always in Kelvin and mole, I get the value of R as 0.08314, okay, which is similar to the value I got in SI units. Okay, so just remember these values, you have to memorize them. As you practice more and more questions, you will find that you end up remembering all these four values. Okay, because usually in your examinations they always give you the value of R, but let's say they don't, then there's nothing you can do about it, right? You won't have time to calculate the value of R, and even if you do, you might mess up the units and the actual value for those particular units of pressure and volume. So it's better to just mug them up. Okay, and let's just review it very quickly. So what we have over here is the value of R in SI unit is 8.314 joule per Kelvin per mole. So if you convert this joule into calorie, we get that SI unit is we get that if we convert this joule into calorie, we get that the value of R is approximately 2 calorie per Kelvin per mole. Okay, and more commonly used unit of R is in liter ATM, where you have used pressure in ATMs and that is atmospheres, and volume in liter. So in that case the value of R comes out to be 0.0821 liter ATM per Kelvin per mole. How do I calculate this value? So it's pretty simple. PV by NT, you just substitute pressure as 1 atmosphere, okay, so, and temperature as 273 Kelvin and mole as 1 mole. So what volume does 1 mole of gas occupies at 1 atm and 273 Kelvin? That is NTP condition. So it is 22.4 liter approximately. So you substitute that value and you calculate the ratio, and the ratio's value comes out to be 0.0821. Lastly, the value of R in bar. So instead of ATM, if we use bar, we have already seen the relationship between ATM and bar. So if we use that relation over here, we get that the value of R in bar liter is same as that in Pascal, except for the decimal point, okay, which was quite obvious also, because the value of bar is simply equal to, in Pascals, is simply given as 1 bar equals to 10 to the power 5 Pascal. Okay, so that is how we calculated this value over here. So now that we have seen the value of gas constant and we have seen what the combined gas law is, we can finally study the ideal gas equation, which is also known as equation of state. Okay, so why is it called equation of state? Because it tells you the state of your gas, okay, or the condition or the present situation of your ideal gas. So this means from here that PV by NT is equal to R, we can simply rearrange them to get the equation PV is equal to nRT. Okay, so just remember here, pressure and volume, they can have any value which you choose, okay, as in any units, alright, but N must always be number of moles of molecules, or for noble gases atoms, and temperature must always be in Kelvin. Alright, and depending on what unit of pressure and volume you are using, the value of R which you use to solve the questions will vary. So if in a certain question you are given that the pressure is 6 atm and they ask you to calculate volume, so since you are dealing with pressure in atm, you use the value of R as 0.0821 liter atm, okay, and then you will get the answer of volume in liter. Okay, and if you want the value of volume in say meter cube, you can convert the liter value to meter cube or decimeter cube or centimeter cube or whatever else you need. Similarly, if say you are dealing in SI units, that is the value of Pascal you are using is in Newton per meter square or in Pascal, okay, then the value of R you use is not 0.0821. Instead of this, you use the value 8.314 joule per Kelvin per mole. Okay, and if you use this value of R, you will get the correct answer of volume in meter cube. Okay, so this is how you deal with this equation. The questions based on this ideal gas equation or the equation of state for an ideal gas are pretty straightforward. Okay, you will be given most of the variables and you have to make the calculations for any one of them. Say for instance, they might ask you to calculate the volume occupied at say SATP. Okay, at SATP calculate the volume occupied by 44 gram of carbon dioxide. Okay, so what you do is at SATP you already know the value of pressure, okay, and you already know the value of temperature. What is the value of pressure? It is 1 bar. Okay, it is 1 bar. What is the value of temperature? It is approximately 298 Kelvin. Okay, and 44 gram of CO2. So pressure is 1 bar. We have to calculate the value of volume V. Okay, and number of moles they haven't given us yet, and the value of R which you will use should be in bar. Okay, so that is 0.08314. okay, bar liter per mole per Kelvin. So the answer of volume which we are going to get is going to be in terms of liter, and temperature is 298 Kelvin. So here we have two variables, volume and number of moles, so we have to eliminate one of them in order to get the answer for the other variable. So number of moles can be eliminated because they have given us mass of the gas. Okay, and since they have given us mass of the gas as 44 gram, we can calculate number of moles of CO2 as mass upon gram molar mass of CO2, which is 44 divided by oxygen O2, so that is 32 plus 12, okay, is 44. So this gives you the value as 1 mole of CO2. So N is equal to 1, and now you know the value of R here and the temperature, okay, and you also know the value of pressure. So you just substitute these values and calculate your answer for volume. Okay, so that's it for today, and in the next session we'll study density of gas. Will deal with some variations of this ideal gas equation and see how we can use it to calculate some other quantities. Okay, until next time, and once again thanks for watching Edupedia World videos.